Hello everyone, I'm Karan. I'm part of software engineering group at Aston Martin Formula One team. My team works with aerodynamics, performance, race engineers to build real-time data-intensive tools. Today, I won't be talking about that a lot because of my NDA, like all Formula One teams. But previously, I've worked with various startups in India building mobile apps for large scale of users, where I tackled offline architecture for almost all the startups that I worked with. So I want to tell you a story today about an offline app that I built which worked perfectly until it did not. This talk is about that journey. We'll explore why offline apps often break and how you can build ones that are truly resilient. You'll learn from my mistakes and check how you can avoid the same pitfalls in the future while you are dealing with offline React Native. So why do we need offline apps? We are mostly connected to the internet, right? Well, for millions of users, reliable internet connection is still a luxury. We often assume constant connectivity, but networks fail, server fail, and people move through dead zone. Offline first apps are resilient by design, handling network failures as the default. This approach builds trust, ensuring users can rely on your app anywhere, anytime. We are talking about making your apps truly available, not just connected. And this is also something that we use in Formula One. This concept is not just for React Native, but it's transferable to any technology that you use. Sorry. Yeah, so out of 4.9 billion users today, nearly 1 billion still deal with unreliable internet connections, and 2.9 billion people are not online at all. As React Native engineers, it is our responsibility to build apps that everyone can use, and not just people with perfect Wi-Fi. To set the scope of the talk, just want to say that we will not be diving deep into complex CRDTs and how to do conflict resolution, but this could be a way for you to design your own CRDTs and make sure it works for your use case. I'm not going to show a lot of code today. Instead, I want to show you how to think about offline first strategy and the problems that I faced. Because building offline experiences is less about clever caching strategies and more about how we model data from the very beginning. So just to quickly check how it is different from traditional applications, we can see that in traditional apps, the user makes an action. We make an API call, wait for the response, it updates the state, and then finally, the UI gets updated. We can see that UI update in this case is the last step. But what if the internet drops midway and you get an error? Offline apps are built with this in mind. You get immediate feedback because you do not rely on the network and use a data storage strategy locally. So when we compare traditional apps to offline first app, we see a fundamental shift in philosophy. In a traditional app, the server is an undisputed source of truth, and it's required for every action. In traditional app, we also rely on the server to show feedback to the user, while in offline first, we use optimistic response, which is instant, and we are going to talk about it a bit later. In traditional app, data flows one way from server to state to the UI. But if the network drops, the app becomes useless. But in an offline first world, the local state becomes the source of truth. The server is just a guest, an optional parameter for async updates. So to cover all the use cases, we first need to be aware of 4 different states where your app could be in. Traditional apps are mostly built for online state, where we assume that we have full connectivity, we sync immediately and get real-time updates. Degraded is a case when your internet is slow or intermittent. We batch sync jobs in this case and reduce payload. So the offline case is the most interesting one, where we have no connectivity, we allow local operations, while traditional apps just can't function at this stage. And then last state could be reconnecting. This is when we start draining our queue of local operations and resolve the conflicts. Right, so now I want to talk about the problem that I faced when I was working in my student placement year in India. This was the feedback that my team got, that the app is really buggy and unoptimized. We are always stuck on loading screens. We spent weeks collecting data like app performance metrics, memory leaks, API performance, to identify what is going wrong. Then finally, we found out that the nature of the business is that the relationship managers are mostly located in basements or dead zone areas, because they were dealing with the inventory of cars. So due to this low connectivity, the app was always stuck on loading, and they see an API timed out error. Turns out the app was behaving as expected. The issue was just the connection. But the users don't care why it is slow. They just care that they can't do their job. So these were the screens that they were mostly stuck on, with loaders and generic errors. It's hard to understand from here that there is a connectivity problem or a genuine issue with the app. So it's better to say to the user that their app is not connected, instead of showing these generic error screens. So then I came up with a solution which I thought was brilliant and could work very well. The solution was using Redux with persistence like MMKV or async storage. The flow was fairly simple. User makes an action. It gets stored in Redux. Redux persists the state in async storage. The app launches again. Redux store gets initialized again with the async store, and then data gets rendered on the screen. I thought, what could go wrong with this solution? This works just fine, and this is what we mostly use in traditional apps, right? But everything went wrong from there. I ended up loading too much data into the memory, and I had no efficient way to query that data. So async storage has a data storage limitation which can be increased, but the inefficient query mechanism was another red flag, since the inventory page has lots of filter based on different car parameters like number of kilometers clocked, the color of the car, make, model, year, and there could be different parameters where you can filter the inventory based on what the client wants to see. So I realized that this approach cannot be scaled further. But we already had the perfect tool for this. We just hadn't thought to use it in this context. SQLite, it is fast and handles a big set of data efficiently. It runs entirely on device, meaning zero server dependency, and it handles large data sets without memory issues. We paired SQLite with Watermelon DB at that time, because the support from the community that time was not really good, but we now have more tools like Drizzle, ORM for type safety, and much better developer experience. We then used this stack to build our app, and it was working fine. We got some good feedback from the users. So I'll just compare the performance for 100,000 records when using local storage versus when we use SQL. So you can see the performance monitor at the bottom. So I'm trying to load 100,000 cars. It's pretty slow. You can see the performance dropping. UI becomes a bit laggy. And then once you filter, takes a lot of time to get back the results of that filter. Took almost 360 milliseconds to get the results. But when we use SQLite with Drizzle, this was really quick, and we did not get a lot of memory issues because it was really fast to work with SQL, because we can use all the efficient things that SQL provides. You can see that filter was just 7 milliseconds with this approach. Thank you. Right, so this solved our inventory page problem where we were just reading the data, right? And we found out that reading is just the tip of the iceberg. In case of read, data was already there. It was fast. We can easily query it using SQL. It is not that complex. But writes, especially in multi-step user flows, are hard if we think of it just as a state. So imagine the internet dropping mid-flow or the app crashing between steps. We were left with partial, inconsistent state in the database. So storing just the current state proved incredibly fragile. We were losing context when things went wrong, and that meant we couldn't reliably recover. This forced us to think differently about how we store data, not just where. So we have already solved the where problem. We need to identify how to store the data. So the problem was that we needed to make a multi-step flow offline. So imagine a customer visits your store and you need to start their process of onboarding them, then taking them on a test drive, getting their documents, uploading it, and then finally you can do different things like exchanging, etc. So there was a complex flow of when user visits the store and to the time when they buy the car. So we needed to make all of that offline. In this case, decision on the previous screen generates the next screen, because once the user selects a car, the next screen of test drive should mention that car, right? You can't mention any other car, but you're not getting any data from the API. So you can transfer it from screen to screen, or you can store it in SQL. So the flow also had options to upload images and videos, like I mentioned. So we came up with the solution of using optimistic response paired with event sourcing. So if I talk about event sourcing, this is where the thinking completely shifted. We realized that the approach, like we were approaching the problem all wrong, and it was the root cause of most of the issues. We were storing the current state, a snapshot of where we are, which is incredibly fragile when things go wrong. Instead, we needed to store what happened, a sequence of events. This simple change makes all the difference, because now we are storing every user action and not just the state that they are currently in. So this is the core insight of event sourcing, and this could be applied to any use case. Like in Formula One, we use event sourcing in cases where there are parts on the track where the car is not able to generate, it is not able to send data because of low connectivity. So you store all that data inside the car and then autofill it when it comes back to the garage. So we can use the same concept, like we are using the same concept here. So this is the core insight of event sourcing applied directly to offline apps. And this new way of thinking opens up so many possibilities. So in this case, for example, instead of storing orders as a row ID, we can store it from the moment that order process started, like adding an item and then submitting an order, making a payment, etc. So let's see it with an example. Imagine a car service booking app. You select a vehicle, you choose a service slot, and then you attempt a payment. And then suddenly the connection drops. App throws a generic error. And this is the state that you are currently in. You have a booking ID and you just have the status, as pending. So what you have lost here is what car was selected, what service slot they chose, and whether the payment was attempted or not. But now, if we replace this with event-based approach, we can see that we have all the information that the user took, even when the app was online, but we still stored every single event with the data attached to it, so that this makes it replayable. We can replay all the events as it happened and retry failed sync operation. We can also come back to the correct screen if something happens during the flow, if you get a call or if you get a crash. So how does it change the data modeling? So instead of creating single rows of bookings with ID, car ID, slot, status, and when it updated at, we can create a table of events. It does not have to be booking only. We can create all the sequence of steps that the user took, and then store it in a way that it is append only, immutable, durable, and it is easily replayable. Right. So we are going from this state-based approach of storing the booking IDs, their state. By the way, I'm using Expose SQLite plugin here to visualize the SQL data that is stored in my application. So here we are just storing the booking ID. We are storing the state the app currently is in. But if we change it with event-based approach, we can see that we create new events. We attach a booking ID to it. We create the event type, like adding to cart, and then we provide all the data that went into that action. So it's like storing a story of everything that happened in your app when it was offline. And then when you connect online, you can start syncing this data to the server, or you can start resolving the conflicts with your data. So it's a pathway to CRDTs. Right. So event sourcing out of the way, we have optimistic response architecture, which I think we have already dealt with. Like most of us must have dealt with it, but just to give a quick brief about it, it enables the app to behave as if the operation succeeded immediately. So optimistic response architecture helps us in providing the user with feedback quickly. We can use it in offline scenarios where we can combine it with locally queued mutation and mocked server responses to keep the UI functional. Once connectivity is restored, these quick actions are synchronized with the backend to ensure that we are consistent. Finally, I would like to say is that what survives offline is what remembers what happened. So most apps store what things are, but offline first apps must store what happened. So the key takeaways are that you need to capture the intent, store event, not just final state. You can use SQLite with Drizzle ORM to give you a scalable foundation, and event sourcing makes our app resilient, recoverable, and syncable. We can also start with a simple architecture and bring complexity when required. I think this is a very important point, because 90% of the use cases might not even need this solution. But you need to have an understanding of when to use it, when to bring that complexity inside your system. And that's all. Thank you for having me here.